The National Electrical Code, or NEC, mandates that overload contacts within a control circuit be positioned on the line side of the control coil. This placement is paramount for ensuring safety and effective motor protection. Consider a scenario where the overload contacts are incorrectly placed on the neutral side of the coil. If a fault occurs that compromises the neutral conductor, the overload contacts may fail to de-energize the coil. This could lead to a continued operation of the motor under overload conditions, potentially causing damage to the motor itself, the connected equipment, or even posing a fire hazard. The principle behind placing overload contacts on the line side is to ensure that any overload condition immediately breaks the power supply to the control coil, thereby stopping the motor. This mechanism works independently of the integrity of the neutral conductor. Even if the neutral connection is severed or experiences a high resistance, the overload contacts on the line side will still open the circuit, effectively shutting down the motor and preventing further damage. While it is a generally accepted practice to avoid breaking the neutral conductor, especially in power circuits, control circuits operating at 120 volts or less represent the specific case where this practice can be modified under certain conditions. The NEC recognizes this and allows for the neutral conductor to be interrupted by controlled devices like overload contacts, provided that certain safety requirements are met. The most critical of these requirements is that the interruption of the neutral conductor must not create an unsafe condition. Placing overload contacts on the line side inherently addresses this concern, as it ensures a positive and reliable means of de-energizing the control circuit in the event of an overload. In contrast, consider the risks associated with placing overload contacts on the neutral side. If the neutral conductor were to become open-circuited upstream of the overload contacts, the control circuit could remain energized through alternative paths such as ground faults, even when the overload contacts are open. This situation could create a dangerous condition where the motor appears to be off but is still receiving power, potentially leading to unexpected restarts or electrical shock hazards. Therefore, adhering to the NEC guidelines and placing overload contacts on the line side provides the most robust and fail-safe approach to motor protection and control circuit safety. It ensures that the motor is promptly de-energized under overload conditions, regardless of the status of the neutral conductor, thereby minimizing the risk of equipment damage, fire hazards, and electrical shock. Let's delve deeper into the practical implications of this code requirement. Imagine a motor control circuit powering a pump in a water treatment plant. This pump is crucial for maintaining water pressure, but it is also susceptible to overload conditions due to factors like debris clogging the impeller or a sudden increase in water viscosity. To protect the motor, overload relays are incorporated into the control circuit. These relays monitor the motor's current draw and, if it exceeds a preset threshold, their contacts open, interrupting the power supply to the motor's control coil. Now consider two scenarios. Firstly, the overload contacts are placed on the line side of the control coil, and secondly, the overload contacts are placed on the neutral side of the control coil. In the first scenario, if an overload occurs, the contacts on the line side immediately break the circuit, de-energizing the control coil and stopping the pump motor. This happens regardless of whether the neutral conductor is intact or compromised. The system functions as intended, preventing potential damage to the pump and motor. In the second scenario, if the overload contacts are on the neutral side and the neutral conductor becomes open-circuited due to a loose connection or corrosion, the control circuit could find an alternative path to ground through the motor windings or other connected equipment. This means that even when the overload contacts open, the control coil might still receive enough voltage to keep the motor running, albeit at a reduced capacity. This situation is extremely dangerous because it creates a false sense of security. The operator might assume the motor is off because the overload relay has tripped, but in reality, the motor is still energized and could restart unexpectedly, posing a risk to personnel and equipment. The NEC requirement to place overload contacts on the line side directly addresses this potential hazard by ensuring a positive and reliable shutdown of the motor under all circumstances. It is a fundamental safety measure designed to protect both the equipment and the individuals working with it. Furthermore, consider the implications for troubleshooting and maintenance. When overload contacts are correctly placed on the line side, It simplifies the process of identifying and resolving overload issues. If the motor trips due to an overload, a technician can quickly verify that the overload contacts have opened and that the control coil is de-energized. This provides a clear indication that the problem lies within the motor or the driven equipment rather than a fault in the control circuit itself. However, if the overload contacts are on the neutral side and the neutral conductor is compromised, troubleshooting becomes significantly more complex. The technician might have to spend considerable time tracing the circuit to identify the open neutral, which could be located anywhere upstream of the overload contacts. This not only prolongs the downtime of the equipment, but also increases the risk of misdiagnosis and potentially unsafe repairs. In addition to safety and troubleshooting benefits, placing overload contacts on the line side also promotes better overall system reliability. By ensuring a positive and reliable shutdown under overload conditions, it reduces the stress on the motor and other components, extending the lifespan and minimizing the likelihood of premature failures. This is particularly important in critical applications where downtime can have significant financial or operational consequences. It is also important to note that the NEC provides specific guidelines for the selection and installation of overload relays and their associated contacts. These guidelines cover factors such as the current rating of the overload relay, the type of motor being protected, and the ambient temperature in which the equipment is operating. Adhering to these guidelines is essential for ensuring that the overload protection system functions correctly and provides adequate protection for the motor. Furthermore, regular inspection and testing of overload relays are crucial for maintaining their effectiveness. Over time, contacts can become corroded or worn, and the calibration of the relay can drift. Regular testing can identify these issues before they lead to a failure and ensure that the overload protection system is always ready to respond to an overload condition. In conclusion, the NEC requirement to place overload contacts on the line side of the control coil is a fundamental safety principle that should be strictly adhered to in all motor control circuits. It provides a positive and reliable means of de-energizing the motor under overload conditions regardless of the status of the neutral conductor. This not only protects the equipment from damage but also minimizes the risk of electrical shock and fire hazards. By following this guideline, electrical professionals can ensure the safety and reliability of motor control systems in a wide range of applications. It's important to emphasize that this principle applies universally to control circuits operating at 120 volts or less, as this voltage level is commonly used in industrial and commercial settings for motor control. While some may argue that placing overload contacts on the neutral side simplifies wiring or reduces the number of components required, the potential safety risks associated with this practice far outweigh any perceived benefits. The NEC prioritizes safety above all else, and its guidelines are based on decades of experience and analysis of electrical accidents. Therefore, adhering to the code's requirements is not merely a matter of compliance, but a moral and ethical responsibility for all electrical professionals. Now, let's consider some specific examples of how this principle applies in different types of motor control circuits. Firstly, in a simple start-stop control circuit for a single-phase motor, the overload contacts would be placed in series with the control coil on the line side. When the start button is pressed, the control coil is energized, closing the motor starter contacts and powering the motor. If an overload occurs, the overload contacts open, de-energizing the control coil and opening the motor starter contacts, thereby stopping the motor. Secondly, in a three-phase motor control circuit, the overload relay typically has 3 sets of contacts, one for each phase. These contacts are wired in series with the control coil on the line side, ensuring that an overload in any phase will trip the relay and de-energize the motor. Thirdly, in more complex control circuits with multiple motors and control devices, the overload contacts are typically integrated into the motor starter or variable frequency drive. These devices are designed to provide comprehensive motor protection, including overload, overvoltage, undervoltage, and short-circuit protection. In all of these cases, the fundamental principle remains the same: the overload contacts must be placed on the line side of the control coil to ensure a positive and reliable shutdown under overload conditions. It is also important to consider the impact of harmonics on overload protection. Harmonics are distortions in the electrical waveform that can be caused by nonlinear loads such as electronic ballasts, variable frequency drives, and switching power supplies. These harmonics can increase the current flowing through the motor windings, even if the motor is not actually overloaded. This can cause the overload relay to trip prematurely, interrupting the operation of the motor. To mitigate the effects of harmonics, it is important to use overload relays that are specifically designed to handle harmonic currents. These relays typically have a true root mean square, or RMS, sensing capability, which accurately measures the total current flowing through the motor windings, including the harmonic components. It is also important to ensure that the electrical system is properly grounded to minimize the effects of harmonics. Proper grounding provides a low impedance path for harmonic currents to flow back to the source, reducing the voltage distortion and minimizing the risk of equipment damage. In addition to harmonics, other factors can also affect the performance of overload relays. These factors include ambient temperature, altitude, and the type of motor being protected. Ambient temperature can affect the calibration of the overload relay, causing it to trip prematurely or fail to trip when it should. Altitude can also affect the calibration of the overload relay as the air density decreases with altitude, reducing the cooling capacity of the relay. The type of motor being protected can also affect the selection of the overload relay, as different types of motors have different starting current characteristics. It is important to select an overload relay that is compatible with the type of motor being protected and that is properly calibrated for the specific application. In conclusion, the proper location of overload contacts in a control circuit is on the line side of the coil as required by the National Electrical Code. This ensures a positive and reliable shutdown under overload conditions, regardless of the status of the neutral conductor. It is also important to consider the effects of harmonics, ambient temperature, altitude, and the type of motor being protected when selecting and installing overload relays. By following these guidelines, electrical professionals can ensure the safety and reliability of motor control systems in a wide range of applications. The application of NEC Section 430.52 provides guidance of sizing fuses and circuit breakers for the motor branch circuit protection. In addition, NEC Table 430.52 provides the percentages to use for the correct protection. Overload protection is also provided in NEC Section 430.31, which are separate devices from the short circuit or ground fault protective devices. These overload devices will prevent damage to the motor when the motor draws too many amps for an extended period. Also, NEC Section 430.83 provides information on motor controllers for horsepower-rated motors. Lastly, to ensure proper motor operation, NEC Article 430 should be thoroughly reviewed and followed.